a molecule is. So here we will discuss what is the quantum mechanical problem related to solving for the physics of a molecule. The take-home message is it's very difficult to do, but there are approximations that we could try to make. So let's look at the simplest thing, diatomic, I call A, B molecule. So A could be H, B could be another H, then we have H2, A could be a carbon, B could be an oxygen, then you have a carbon monoxide, okay? Doesn't matter. But that is the simplest class of molecular problems. Here, let's start from macroscopic thing. So here is a jar, okay, a cylinder, okay, with many molecules in it. That is your thermal and statistical mechanics setting. So you have a system with n molecules, okay? So here you look into it. If your eyes are very good, okay, you will see a diatomic molecule. Otherwise, you'll see a point charge. Then, what is there actually? So you look at this, blow it up, so you have this, okay? So this is the problem that we want to look into. We have two nuclei, many electrons, usually 10, 20, 30 electrons. Then the problem is, how do the electrons distribute themselves? If we know that, we know the wave function square, then we can shade it in some form. This is the electron density at different places. Then we see how the electrons play the role of binding the nuclei to form this molecule. So we will look into that. And after the electrons forming the bond, a simplified picture emerges. The electrons will be responsible for this spring. Then we can look into vibration, rotation, things like that, okay? In your statistical physics course, if you don't worry about this internal degrees of freedom, you will have a jar of gas, n of them, and then you think, I don't see that. I only see the whole molecules flying inside the cylinder, okay? And for that case, you have the mean energy being 3/2 nkt. Okay, so do you know that? You had your midterm, right? Okay, n is the number of molecules, T is the temperature, okay? Now, if you're thinking about this, actually, you are looking at the center of mass motion only, okay? This is this picture. You don't see the internal vibration, rotation. You only consider the center of mass of this AB molecule, taking it as a point particle, fly apart. This is the free particle statistical physics, okay? Now, if you go into deeper and do the vibrational statistical physics and the rotational statistical physics, okay, then you will see they do have additional contributions to the heat capacity, okay? Therefore, you will have some temperature variation of the heat capacity in molecules in addition to monatomic gases. So we will be doing the same strategy. In quantum mechanics, we don't care about the center of mass motion because after you do the relative mode, the center of mass coordinate and then the relative coordinate transformation, the center of mass motion is free. It's freely moving. And we are not care about that part. We want to understand binding. Okay, so therefore, we don't care about that. We did that for atoms, actually. Nucleus, several electrons, even hydrogen. In principle, it should be something like that. Even the nucleus is slightly moving, okay? But we don't care about this by replacing the mass by the reduced mass. So let's look at the full Hamiltonian, all right? I flashed it for you, rather scary, okay? But let's look at it. So think about a diatomic molecule. You have two nuclei. So I put it plus here and another plus, all right? They could be different atoms. So this nucleus would have ZA charge plus ZAE charge, and this has plus ZB charge, okay? So follow me. Z is the atomic number. Therefore, atom A will have ZA electrons. Each one is minus E. Similarly, atom B will have ZB electrons. These are the dots here, okay? So you have that many ZA plus ZB electrons. So you count all the things, rather scary. You have a ZA plus ZB plus 2 particle problem, quantum mechanically. Now, in quantum mechanics, the first thing to do is to write down the Hamiltonian. Hamiltonian is simple for us, it's just the total energy. T plus V, okay? Kinetic plus potential, that's it. So let's look at how many kinds of terms we expect. The nuclei can move, so they have kinetic energy. All right. Then each electrons can move, so we have kinetic energy of the electrons. So far, so good. Then each electron will see nucleus A, so this is a Coulomb attraction. Each electron will also see B nucleus, so Coulomb attraction. Each electron will see the other electrons, Coulomb repulsion. Nucleus B will see nucleus A, Coulomb repulsion. All right, so do you follow? Do you see any other extra term? Okay. Okay. Therefore, we can start writing down things, right? For example, Ke of nuclei is easy. So it's the momentum A squared over 2ma. So that is the kinetic energy term for nucleus A, right? Something like that. So don't be scared when you see the next page. So this is the Hamiltonian and thus defined the Schrödinger problem for a molecule. I use different colors to stress the nuclei stuff and the electron stuff, okay? That's why there you see two kinds of things in one expression. Here, these two terms, I hope that you can easily see they are the kinetic energy of the nuclei, okay? Now, this is important. You don't see that in atoms, okay? For the reason, Atoms will only have one nucleus. We flow out the center of mass, then we can fix the remaining that nucleus with a reduced mass representing the relative motion. You can fix that atom, that nucleus at 0, 0, 0. Therefore, you don't see this. Okay, you must understand this point. But for molecules, we cannot avoid it. Well, you may think, I haven't used the reduced mass to throw out one thing, right? Even you throw out one thing, the other remains. You have two terms, okay? And we need them there for the reason. I have been trying to convey that in molecules, there is a part of the problem has to do with the nucleus vibration after some bond has been formed and the nucleus rotation. You see, they move, vibration, rotation, all right? We need them here in order to take into account of these two new elements. So they are good. They should be there, all right? Then we have the kinetic energy term of the electrons. Now, if you don't follow the symbols, please ask, okay? I'm trying to use the most common symbols. The small m is the mass of an electron. The big M is the mass of the two A and B nuclei, all right? Here, I already substitute the operator. So you see this minus Laplacian that has to do with the momentum operator for the electron. This is the momentum operator for B nucleus for A nucleus square, okay? So far, so good. So these are the two kinetic energy terms. There are many terms, okay? Altogether, they are ZA plus ZB plus 2 terms, all right? You have that many particles, therefore you have that many kinetic energy terms, fine. Then I write down a nuclear repulsion. So there are that many positive charge, they repel, it is plus, okay? Then it is Coulombic. This is the separation. We don't know the preferred separation. We want to find that out. So this is just a Newtonian to set up the problem. Just to be very strict in quantum mechanics, at this point, this RA and RB are actually position operators of the two nuclei. Okay, do you follow this comment? Understand? I have momentum operator for the nuclei as well as, of course, conjugate pair position operators of the nuclei, all right? Now, this is at least correct for this expression. Then let's go to the next terms. Every electron, now I use N to represent the total number of electrons. Every electron will see nucleus A, okay? It is attractive. It is Coulombic, okay? So Ri is the position operator after using Schrödinger's representation, the substitution. This is the electron's position operator. This is nucleus A position operator, all right? So this is the every electron sees A. Similarly, every electron sees B, okay? And the last term is the very bad guy. We have electron repulsion, but we have seen that before. Even in helium atom, we have this term, electron repulsion, okay? But here we have many pairs of terms. We have n electrons, okay? Pay attention to the plus minus sign. Now this is repulsive, attractive, and this is kinetic. Okay, so any question about equation 1? This is the problem. This is the problem of a molecule. Okay. You can easily generalize it to any molecule now. You can write it down, okay? So that's the point. We know the physics, we just don't know what to do with it. We know the governing equation, we just don't know what to do, how to solve it, okay? Now let's inspect this Hamiltonian. Here, in a shorthand way, I would like to stress the Hamiltonian, just like classical mechanics, it has all the position and momentum pairs of the electrons and the two nuclei inside it. Okay, so everybody understand this statement? Okay, now you have P, you have the capital P nuclei, you have the small p electron, you have capital R, the position of the nuclei, you have the small r, the position of the electrons, okay? Now the key point is this bracket function, it has all this thing inside, all right? Shorthand notation, I will use this for all the electrons. There are so many of them, I don't want to write that, okay? So let's write down the total, the full time-independent Schrödinger equation to solve for a molecule. H psi equals E psi. All right, now nothing fancy, we know that, but it is worth looking into what all this symbol means. I want to emphasize that we are solving for the allowed energy of the whole molecule. This is the E molecule. I included a subscript total there. By that, I mean, later on, we will make approximations. For example, we will suddenly neglect all this for how? Pretending the nucleus do not move, fixed at a certain distance. Then suddenly this operator becomes, the kinetic energy for a moment becomes zero, don't move, and then the position is just a parameter. A is here, B is there, no longer operator, okay? So suddenly we will freeze this for, and then look at the electronic part of the problem. We will get some eigenvalues, they are called electronic energy, but not the total yet, because as I try to convey throughout today, there are additional energy, vibration and rotation. Only when we add all this together, we have the total allowed energies of a molecule. Just like all other Schrödinger problems, we will find many allowed energies. Very close, very densely spaced, okay? We are going to look for that. That is our goal, all right? But at this point, there's no approximation applied. So it is the full Hamiltonian, and therefore this is the total energy of the molecule. This is what we want to get. Similarly, at this point, this is the total wave function of the molecule. Not only about the electron and not only about the nuclei. It is everything combined. Okay? Just like any Schrödinger problem, in the Schrödinger representation or the Schrödinger equation, the Hamiltonian carries all these conjugate pairs, where the wave function will be a function of the coordinates. Okay? So the electrons will be R1 to Rn. The nucleus will be a function of the position of the two nuclei. All right? So, although equation 3 looks very common, trivial, but you must understand the complication of this Schrödinger equation for a molecule. Okay? So any question up to here? Equation 3. Okay? In contrast, for helium atom, we don't have this. Okay? We only have the two electrons, kinetic energy, and the coordinate. And we don't have this. Okay? We only have psi helium atom R1, R2. So you see how luxurious we have been, how easy that helium atom problem is, although it's still not solvable. Okay? So now we get used to the fact that, hey, there's no analytic solution. Let's try our best to find some way out. And that is the art of doing physics. Okay? So basically we are done. We have written down the equation, find some postdoc, solve it numerically, everything is done, okay? But are we really done? It cannot be solved for any molecule, not even H2, okay? Now, some of you may be very clever and say, okay, you are making the thing too complicated. How about this? For the two nuclei A and B, you form a center of mass, coordinate, and a relative coordinate. You throw out the center of mass. Okay, that is freely moving. Then you get one fewer term. All right? Good, good. But that doesn't help much, but it is useful. We will do that. Okay? So that is what I'm trying to say here. For this nuclei part, you may do a reduced mass and a relative coordinate. You throw away the center of mass freely moving thing, and then you have one fewer variables. So you reduce it from n plus 2 to n plus 1. Congratulations. Okay. With that, I rewrite the whole thing for you. So this is really our problem now. Diatomic, okay? Now this is diatomic. Here you don't see RA, RB anymore. We only have a relative motion. Remember, the capital R is the relative. You sit, the picture is that you sit here. I try to draw it, okay? You stand here and you look at the other one. So you stand at A, look at B, you call this separation R. Okay. After you throw out the center of mass motion, then write the whole thing again. You have this one kinetic energy term. That's good. You still retained. You sit, you stand at one. Okay. You sit at one A. You look at B. So B could be moving, vibrational relative to you. So that is the vibrational thing. and B will be rotating about you. Okay, follow me? Or rotating around you. Okay, so that term is sufficient to carry this vibrational and rotational motion. That's good. Okay. So with this simplification, flow out center of mass term, the Schrodinger equation becomes this. I just rewrite that using one fewer variables. Okay. The wave function becomes, instead of RA, RB before, just a relative distance, a relative coordinates between the AB nuclei and then all the electrons. It is identical to the previous one, just reducing, throw away the center of mass thing, okay? Now, it is time to discuss the difficulty in one line. As I emphasize all the way along up to this point, this is the momentum operator of the nuclei, and these are the position operators of the nuclei. Okay. At the same time, you have kinetic operator for the electron and position operators for the electrons. Everything goes together, and in particular, look at such terms. Do you see the electrons' coordinates coupled with the nucleus coordinate in a very bad way, 1 over this distance? You cannot separate these Coulomb terms, just like we cannot separate the Coulomb term in helium atom between 2 electrons, okay? This is bad, we already know in helium atom, but this adds to the situation to make it worse, okay? So this is the point I try to make here. They're all operators and they coupled, okay? Now, all in all, what I'm trying to say is the following. This H total cannot be turned into something like a part of the Hamiltonian that has to do all with the nucleus, the nuclei, and then plus another part of the Hamiltonian that only has to do with the electrons. Okay? Do you get my point? That is not true. Do you get my point? Okay, now this is a very important conceptual point, all right? If we can do that, then we can use separation of variables. But in principle, we see all these coupled terms, very bad stuff. We cannot do it. Okay, do you get that point? So therefore, formally, I emphasize the word formally here, okay? The total wave function, because we cannot separate the Hamiltonian, this total wave function formally is a function of all these coordinates together, okay? And definitely, you cannot write it as a product of nucleus coordinate wave function times a electron coordinates wave function. That is in principle wrong. Okay, do you get my point? Hello? Do you get my point? Okay. Are you there? Are you there? Okay. All right. Okay. Now, we have seen that before. In helium atom, in principle, the wave function should be R1, R2 together. And we shouldn't expect that to be written, can be written in terms of something called phi 1s R1, phi 1s R2, something like that. Okay, and then multiply a spin singlet. Helium atom, when we do that, we are making an approximation. Okay, do you follow me? Okay, so this is not something entirely new, all right? But here's the point. We know what is not right. Maybe that's a way to do physics, okay? So we know that formally it is like this, not separable. Formally, you cannot do that, okay? But we see the advantage of doing that. If we can separate the consideration into the electron part and the nucleus part, that will be nice. You may think that this is our wishful thinking, but I think that is how physics is done. You first think about a way out, and then you explore that way, and then you examine whether that strategy is effective, reasonable, give you good results or not. Okay? So now, the very last line and this section. We know that equation 6 is in principle wrong, but we want to do it. Okay? So we are going to make an approximation that this molecule's total wave function can be represented by a product of two parts. It is the nucleus motion part, the first term. I use the subscript n here, sorry for the multiple usage of n. Here I mean nucleus, okay? The subscript here means nuclear motion, okay? It's not the total number of electrons. It means the nuclear motion multiplied into a function that has to do with the electrons only, all right? So now, at least, in the very last equation, I motivate this strategy that will go through the whole chapter, the whole module, okay? We are going to try to separate the consideration of a rather complicated total molecular wave function into electron part. We will do that first, and then the nuclear vibration and rotational part. All right? So, any question up to here? Any questions? 有冇問題？有沒有問題？ Okay, up to here. Okay? Now, in the last section, one sentence summary is that A, I try to bring out the complexity and the difficulties of the full molecular problem. Second, I motivated a way out of this trouble. Okay, so any question? Oh, I run out of symbols actually. I know that is bad notation, but first of all, I want you to understand what I try to say, okay? I know what you are saying. I am balancing clarity and the symbols. Okay, I think you are asking about this one, are you? Okay, if I want to do it, actually, I should put this now. I am standing here at A, and then I'm looking at B. All right, so this is my R vector. If I do that, then this is 0. Do you see? Okay, and then this is R. Do you see? Okay, but that seems to, I tried that, but then it lost the idea that I still have 2 nuclei. Do you understand? I want to convey that it's not separable. That's the point. All right. Okay, so it is not meant to be really using this to do calculation. Do you get that? Okay. If I get the physics correct, I will be very happy. Conveyed it across. All right. So any further question? Okay. In principle, it does, but then we have to think about the moment of inertia, first of all, okay? That is not significant. Then more formally, we need to think about, by rotation, how many degrees of freedom are there? All right. For example, AB molecules is linear. So by rotation, actually, we mean how many angles do we need to specify the orientation, right? Rotation means it could be pointing anywhere. Okay, do you follow me? Go. Okay, therefore, the question becomes a classical mechanics problem. Give you a rod. How many angles do you need to specify the orientation? Okay. For a rod, a straight line, I think you need only 2 angles. A theta and a phi will do. All right. So therefore, you will have these 2 rotational degrees of freedom. Okay. So that is the formal way to think about it. Okay. But don't worry. Don't worry. I don't want to rely too much on the other knowledge so as to wash out the beauty of the quantum mechanics treatment. All right? Don't worry. We can count it later. All right? Now, I would like to introduce a little bit about this, I would say, should be Nobel Prize winning approximation. That is exactly what I motivated a few minutes ago. This falls into the name of Born-Oppenheimer approximation. Okay. Now, for those of you who want to organize our class notes into more systematic way, you may cross-reference this section again to the approximation methods. We have been introducing approximations here, there, okay, apart from the perturbation theory and the variational method at the very beginning. So this is another very nice physical insightful approximation. This is under the name of Max Born and Robert Oppenheimer approximation. Any one of you have heard Oppenheimer? A very famous physicist. Do you know? Well, there's a very, right. He's the atomic guy, and then after the war, he was regarded as a kind of his incarnation to communists and then the US government. Now, he had he's responsible for the atomic bomb project, okay? And then the Congress of the US government after the war grabbed him into hearings and then asked him very tough questions about his loyalty. And then he was his so-called security clearance, I mean, looking at those high top secret documents, was taken away after the hearing. But then Princeton's Institute of Advanced Study came in to hire him as the director in the 1960s, maybe 1950s, late 1950s. And then when John F. Kennedy became the US president, he was awarded the highest medal for science in the US as a way to, as an apology for the harsh treatment of on him after the war. He made good contributions to the US during the war, the atomic bomb project, okay? You can imagine, under him, during the atomic bomb project, were those people like Feynman, Hans Bethe, Fermi, okay, all under his management. So this is Oppenheimer. Max Born, again, a very, I think, influential quantum physicist. Heisenberg did the quantum mechanics under his supervision, basically. So, Born-Oppenheimer approximation. Let's look at what it is. The whole point is we do want to make this approximation. Okay? Now, notice that here I introduce a parameter to label this separated electronic part. What do I mean by that? Let me introduce the basic idea of Born-Oppenheimer approximation. Okay, now, the first thing I would like to tell you is this Born-Oppenheimer approximation is so important. Without it, we don't have molecular physics. Without it, we don't have the whole field of solid-state physics, because the same approximation is used in understanding solids. Why do we have energy band? Why do we have band gap, etc.? Okay, so let me explain the idea. The derivation or the justification is beyond our scope in this course. So I just want to convey the picture, okay? His idea is as follows. The real molecule has nucleus, 2 nuclei, and some electrons. But the electrons has a very light mass. It's much less than the mass of nuclei. Okay? Maybe 2,000 times or, okay? Now 2,000 times is the worst scenario. What I mean is that it is just a proton. So if you have H2, then you have proton. But ordinarily, you have a heavier atom, right? That could be easily 10,000, 20,000, 30,000 times. So here is Born and Oppenheimer's idea. They are thinking about this. Since the electron has so light a mass, as they try to explore this potential landscape, or in a more classical physics way, the motion of the electrons will be at a very short time scale, okay? Compare with the, do you see my slow motion of the nuclei? Okay, so that means it is like someone running very fast and the track is maybe slightly expanding, contracting. So the person will run many times is still that 400 meter without noticing there is a 401 meter on the track. That is something like that. So they are thinking that as for the electrons viewpoint, the two nuclei as if they are fixed in location. Okay, that is the point. Okay, so do you get the point? So they are motivated to do the following. Let the two nuclei be fixed in location. So no longer there are nuclear motion, okay? And we don't need to take them as operator. They are just a parameter. I fix it there, there is a separation. That is just a number, 1.3 angstrom, okay? There, you do the electronic problem. You solve the Schrodinger problem for the electrons. Then, that's not the end of the story. You try 1.2 angstrom separation. So that is another problem, another value of R. You do the electronic problem, you get other solutions. Then you try 1.1 angstrom. That is another problem. You try to solve this electron problem, you get another solutions. Okay, do you follow me? You understand? At least the big picture. Okay? So that is why I put it out there and I emphasize that it is not an operator. It is just a parameter. You give an R to define the problem. R means the separation now fixed for the moment only. Later on, we will take that nuclear part out and do something on it again, okay? So let me summarize today's with the punchline, okay? So we are, now, here is what that 1.1 angstrom, 1.2 angstrom parameter is, okay? You do that, each is a problem. So, when we don't allow the nucleus to move, then we throw out the kinetic energy term. We have this electron hematonia. This is the electronic hematonia. We only have the electrons kinetic energy. We have the electrons position operator. RA, RB, and the separation is now a number. You give me fixed there, okay? We still have the bad electron-electron repulsion. So you give me a separation, it is a problem. You give me an other separation, it is a problem, okay? So let me represent it in this picture, okay? You try R1, a problem. You try R2, another problem. You try R3, another problem. So what is the consequence? You try R1, the electron problem gives you many eigenvalues. You dot it here. R2, then you get many eigenvalues. You dot it here. R3, you do it, many solutions, okay? You keep on doing that for many values of R. Guess what is the end result? You see something like that, okay? Therefore, the electrons serve to select a particular preferred separation of the nuclei. And that is the story behind how electrons are responsible for forming the bond. That will be how strong the bond is. That will be the preferred bond length. The nuclei will be preferred to stay at that particular equilibrium separation. The calculations try the different separations. Okay, so I will stop here today. I conveyed you the big picture. That is how we understand chemical bonds. electrons are responsible for bonding. Later on, we will try to see how we can solve this actually rather complicated electron problem. There are still many electrons in there. How to do molecular orbitals problem on this electronic problem. But the story ends this way very beautifully. You have this set of curves. You can see whether you have bonding, okay? You have heard bonding, anti-bonding stuff. We can see how they come up from Schrödinger equation, okay? So that is the idea, okay? The next part will be, after you do that, you see, the nuclear will start doing the vibration and rotation about this minimum. And that is the other term that we have not considered so far, okay? Very interesting physics, very involved idea, but at the end, it's not that complicated. So I will stop here today, and then I will stay for some questions.